Things are first.
Yeah. Okay. Good afternoon, everyone. Today we are going to perform the Zener diode. First of all, we will study what is Zener diode and what is the characteristics of it, and then application of it, direct application of Zener diode as a voltage regulator. So, due to COVID situation, now we are not in our campus, so that's why there will be no physical components, recordings, those were presented in last labs. So only visual things will be there, means online things will be there. So first of all, we will try to demonstrate the Zener diode experiment in virtual lab. Then we will try to, if time permits, then we will try to draw the circuit in that simulator. I already introduced to you people. So there we will try to draw this circuit and you people can explore it on your own space. Okay. So I think all of you are familiar with Zener diode, right? You people are familiar, right? What is Zener diode? Means it is basically a special purpose diode and the characteristics, the basic difference you can say, or that prime most difference is that in PN junction diode, the reverse bias, there will be no current. But in case of Zener diode also, in reverse bias, there will be no current until a particular voltage. That voltage is called breakdown voltage of that Zener diode. So basically, if you put a Zener diode in a forward bias, then there will be no difference with the Zener diode and normal PN junction diode. If you put it in a reverse bias, then you will see something different that is, or something unusual that is not present in PN junction diode. So in case of PN junction diode, we have already shown you that if we keep on increasing the reverse bias, still there is no current or almost negligible current. But in case of Zener diode, that if we change the reverse bias after a certain voltage, that is called Zener breakdown voltage or VZ. So in a regular basis, our lab, those Zener diode, they are having a breakdown voltage around 5 volt, 5 to 10 volts, something like that. So there are different Zener diodes with different breakdown voltages. So at that voltage, you will have a current conduction, though it is in reverse bias, but at that particular voltage, you will have a current conduction. Means you will have sharp changes in current as in similar to the forward bias. Okay. So after that, after checking that characteristics of the Zener diode, we'll see, and then we'll study two most important thing or application, direct application of it. Zener diode is voltage regulator. Means a voltage regulator means it will be a device. If we change the input as well as the output, but the voltage across it will should be same. Means there will be two kind of changes. If you change the input voltage, then also there will be no change at the output voltage. And if you change the load current, load means, in general, load means those uh, passive components, those are connected to a particular source, those are called load. So in our case, we will use a resistor as a load and variable resistor for load regulation. So what does it mean, regulation? I think the theory portion you people are familiar, but still I am telling you a little bit about it. So line regulation means then we are going to change our input voltage. Depending on that, we will check what is the output voltage across this generator. Yes, the condition should be that, obviously, if you want to have a Zener effect, then your voltage across Zener should be uh, greater than that of your breakdown voltage of that particular Zener. Otherwise, it will not act as a regulator. So that will be line regulation. So and I think you are familiar with these formulas and no issue with this one. If you have any doubt, you can ask me, means after the class or after in next lab. So the thing is that after line regulation, we will have a load regulation. In load regulation, what we will have, we are going to vary the load current or load itself. So if we vary the voltage resistor, then obviously current will change. So then, but still the voltage across it should be same. So what does it mean? Means why it is required basically? Basically, suppose we are mm, supposed to we are trying to design a voltage source, constant voltage source. So means the ideal voltage source should be a particular voltage means as a source that will maintain always that particular constant voltage irrespective of how much current you are drawing from that circuit. Suppose means what does it mean actually? Suppose you have uh, connected a 1 ohm resistor to a voltage source of 5 volt. In that case, the voltage across 1 ohm should be 5 volt. And let's say you have applied a 1 meg ohm, then also it should be 5 ohm, sorry, 5 volt. And you have applied 10 ohm, then also the voltage across this resistor should be 5 volt. So that is expected. But in general, we have to design precisely to have a particular voltage regulator in that form. So basically, Zener diode will help. So in practice, not only only Zener diode can control this. There are so many things and drawbacks. But in for basic purpose, we can say it will act as a voltage regulator. So that is why these two characteristics is needed: line regulation and load regulation. Okay. So till now, any query? If you have, then please ask. Then we will go for simulation. You can unmute yourself or you can ask through chat. If you have any query, then please ask. Till now, any query? Anyone? Okay, good. So first of all, we will study the Zener diode characteristics. Okay. Then line regulation one and load regulation. Okay. So the circuit symbol for a Zener diode is something like that. In case of normal diode, it is a straight line, but in case of Zener diode, it will be like this. And it is on the electrode notation is quite similar to that of a normal PN junction diode. This side is P side and this is N side, or anode or cathode, you can say like that. So as you can see, our P side is connected to the source of a negative side, means in reverse bias, and positive one is connected to the N side. So it is in reverse bias. So what we are going to change, we have to choose. Okay, there are some so many that in previous case also you have seen that different different diodes are there, different PN junction diodes are there with different names with different specifications. So in this case also we are having different that Zener diode with different code. It is not required that you have to memorize all the code, but still it will be better useful for you if you can remember. Then depending on the application, suppose in your project you need a voltage regulator of 7.5 volt, then you need this Zener diode BZX5 C7V5 7.5 volt. So depending on that valuation, that specification of the diode will be different. So as I already told you that it varies in general 5 to 10 volts in between. So there are 3.6 volt Zener diodes are also there. Depending on that, let's say we are interested in 7.5 volt general breakdown voltage. Okay. So the experimental setup will be that. So we are going to change the voltage of the source as this total source is connected to a variable resistor, or you can say potentiometer. Depending on this connection, depending on this means value of this means point of contact of this potentiometer, we will have different voltage across this Zener diode. So we'll see what will be the characteristics for it. Okay, so it is in only it is in this case we can have only that reverse bias configuration, not that forward one. So in case of forward bias uh, and reverse bias, we'll draw here and we'll check. So first check it for only reverse bias. So let's put the rheostat in 25 5 ohms or something. Okay, 11 ohms. Depending on that, you can see there is no current. Voltage is 1.316 volt. Okay, add it to the table, then increase the rheostat again. So by changing this RH value, basically we are changing the voltage across this diode, nothing else. So okay, so for 6.2, we are having current in milliamps, 0.003 milliamps. So current starts conducted at 3.588, that is in microohm, means 1 microohm, then 1 microohm, 6.27 volt, it is 3 microohm. Then as the voltage is 7.5 exactly, and the current is 8 microohm. Now we are going to change it. So we are changing the voltage, changing the rheostat, but the voltage across it is constant. It is not changing. Okay, so and if we plot it, then we will have it. Uh, the value is not, means graph is not so smooth. Basically, the characteristics will be like this. Yes, the characteristics will be like this. So for in case of forward bias, it is similar to the normal PN junction diode, and in case of reverse bias, the after breakdown voltage there will be sub current. Otherwise, it will act as a normal PN junction. So this will be the complete characteristics. As we in this case we have considered that particular points vary in means in different steps, greater steps. That is why we are having this kind of curve. If we plot it, and we will see in a simulator also, we'll have a nice curve as similar to this one. This one. Okay. So we can change, or let's say 5.6 ohm, 5.6 voltage Zener diode with 5.6 voltage breakdown voltage. Now change the sorry, clear everything. Now choose a diode, then add it to the table, then your state value is increasing. So basically the voltage is changing. as we are increasing the voltage across the diode. Basically, current through it is also changing, and so as you can see, once it reaches to this particular value, then the voltage across it is not changing. So you can plot it. So the graph is not smooth, but you can have the idea about that nature of the curve from here. Okay. So till now, any query? Do you have any query? You can ask me directly by unmute yourself or through chat. Okay. Let's go to that line regulation one. I hope you people do not have any query. So I am moving forward for the line regulation one. So in case of line regulation, basically it is short form line voltage regulation. Line voltage means the input voltage is the line voltage. So for line regulation, we need this circuit. So where we have three ammeter and one voltmeter. Okay. So why this ammeter is for? This ammeter is for to measure the current through it, and as because we are changing the DC voltage, so the current through this resistor will change, and depending on that, the voltage across this Zener diode also will change, and we are going to measure the current across the current through the Zener diode, and also this is our load. This is load means load resistance is connected. So we are going to measure the voltage across it, and as well as the current across. Okay. Okay. So the unit means fixed unit is given. So for series resistance and load resistance, the unit should be in kilo ohms. Means whatever value we are going to put, that will be in kilo ohms, and we'll see what is the nature for that. Let's start with 1 volt and Zener diode. Let's say make a Zener diode constant. Yeah, we are going to, let's say for 3.5 volt, right? We're going to make it constant at 5 volt. So our our Zener diode will maintain a constant voltage of 5 volt. Yeah. Okay. So this is Zener voltage, and we have to choose this. Okay. Okay, so for this case, what we have selected, our DC voltage is 1 volt and Zener voltage is 5 volt constant, and resistor is 100 ohms and load is also 100 ohms. Okay, then add this value to the table. Okay, then what we are going to do, we are going to change the DC voltage. So let's change it, add it to the table particular value. As we are increasing the voltage, value is changing. As you can see, once we cross that Zener voltage, our input voltage has changed or raised up to Zener breakdown voltage, then the regulated output voltage is always constant. Yes, that is the thing I told you, that beyond this voltage, all the voltage across the load will be constant, but below the breakdown voltage, let's say in case of we have selected 5 volt as breakdown voltage, so below it the voltage is not constant as 5 volt. So we are going to design 5 volt 5 volt voltage source. So in this case, that is why we have applied the 5 volt Zener diode. Now also you can change the value. Let's make another change. So values are changing. So we have, as you can see, we have changed our input voltage from 1 volt to 23 volt, and let's go to the maximum one. Yes, maximum one is 30 volt. Still the output voltage is always constant. If you can see the output voltage is always constant. Now we are going to plot it. Let's plot it. Why is not showing? It should be. Okay, I don't know why it is not showing.
Sir, it is showing.
It is showing.
Yes, sir.
Graph is visible to you people?
Yes, sir.
Is it?
No, sir.
No, sir.
Okay.
No, sir.
Okay, good.
There
Thanks.
is empty.
Actually, he is saying your screen is visible. Maybe that the graph is not showing.
No. Okay. I don't know why. Maybe let's paint it. Then let's check it. Is there any view we can see? Yeah, that is maybe due to the problem of the server. Otherwise, we can plot it in any graph plotter. No, it is not showing here. Okay, that is maybe due to this issue. So what is this is our output voltage and this is source voltage. So means this column, output voltage column, unregulated supply voltage, sorry, this is input voltage, unregulated supply voltage, and output voltage, regulated supply voltage. So let's plot it. Then you will have a clear picture. No need to plot through this software. I am used to this one. That's why I am using. You can use something else. Even Excel also you can use. Or also you can use Desmos or GeoGebra for drawing any graphs or something like that. Okay, it will take a little bit time. Okay, till now any query? Then we can discuss on that. Then we can plot it. Do you have any query? Are you getting at least or not?
Yes, sir. Getting.
Okay. Let me, don't think it will copy it. So we need only this one and this one, right? This would be 1. But 50 volt from is getting okay. So
So are you using any other thing? It will be not visible. You have to stop share. It means if you have using Excel or anything,
okay. So my screen is
you
not
have to stop this. Yeah. You have virtual lab screen is visible. If you are using anything, any other window, you have to stop to share this thing, and then again you have to share the screen with that window.
okay. Okay, I'm going to share it. Just a moment.
Okay.
I'm plotting it and going to share it.
Okay.
Now is it visible?
Yes, sir. Yes, sir.
So what I have done, this is our input voltage and this is our output voltage as it was given here. We have taken the data from that experiment V lab. Now we are going to plot it. The graph is not quite smooth, but still you can have a look that it is after a certain voltage. Once the 5 volt is there, then you can have that smooth constant voltage curve. So, and one thing, let me add the grid, then only you can clearly see. Yes, as you can see, this is 5 volt. After 5 volt, as we are changing the voltage, the input voltage, but still the output voltage is constant. So this is for simulation we are getting, and this is all these are based on equation. That is why we are getting this type of constant. In real example, there will be deviation, and it is not like that. Means not that much smooth, but still the voltage across it will be little bit constant in case of Zener diode. So this is the case for line voltage regulation or line regulation. Okay. Now go to our VLab screen. Now VLab screen is visible, right?
Yes, sir. Yes, sir.
Okay. So this was for all these are for that VLab line regulation. Now go try for that load regulation one. Okay, so for this one also we have to set, no, for this one the circuit is different. Instead of varying a variable voltage source, in this case we will have a constant voltage source, but variable load. As the load is varying, so our source should be independent of load. The main motive is that maybe our input may change or maybe our load may change, but our source should be constant. So that is why we are trying to plot it, that line regulation and load regulation. This. So in case of load regulator, we will have a variable resistance. So this is the difference, as you can see from here. So in case of line regulation, we have that variable voltage source, but constant load. But in case of load regulation, we'll have a variable resistor or variable load, you can say, but voltage is constant. So in similar fashion, let's say our the Zener voltage is 5 volt, and in this case our resistor is 500 ohms. Okay, for 65 ohms, and load voltage we are going to change, sorry, load resistor we are going to change, and DC voltage should be above that Zener voltage, Zener breakdown voltage. Okay, otherwise we will not have the effect of Zener diode. So let's say our Zener input voltage is 24 volt. Okay, 16. Yeah. And now we are going to change the series resistance. Let's put it some value. Series resistance is 1 kilo ohm. Okay, then 500 ohms. Okay, 5 ohms, and now we are going to vary the load resistance. So let's say initially our load is 20 ohms. Add the values to the table. So our DC voltage is 20 volt, Zener voltage is 5, and that series resistance is 505 ohms. Now change the RL value slowly and add all these data points to the table. So then, as you can see, we are adding the load resistance value, different load resistance value. Depending on that, we will have different load current and Zener voltage. Zener current is this, but Zener voltage is this much. Okay, so this we have added already. This thing. Now have some other values and the final one. Good. So now let's check whether no. Still the plot is not working. Okay, then we have to plot it again. So in this case, we have output voltage and load resistance. So we have to consider this voltage, this one. Let's copy this data. And now okay, I'll share you after drawing the graph. Just a minute. So I'm going to plot all this data in the same table. Same graph, it will be better for you people. So in this case, our resistance will be in x-axis and output voltage will be in y-axis. So one second. I'll share the screen with you people. No issue. Now is it visible, right?
Yes, sir.
Okay.
Yes.
So this is our load and this is our output voltage. in obviously unit in volt P, and this is in ohms. Okay, now plot this one. Now it is completely smooth curve. So as the load voltage is load resistor is changing in ohms, but still the output voltage is constant, maintaining a constant voltage of 5 volt. So this is basically load regulation in case of Zener diode. Okay. Any query? Do you have any query regarding this load regulation and line regulation? If you don't have, then we'll go for that circuit one. Do you have any query, or we can move to that circuit drawing part?
Yes, sir. Please explain why the voltage become constant across the Zener diode this time. I understood it as a line regulator, but in this I didn't understand.
Okay, load regulation you cannot understand, right? Okay.
No, sir. I understood, but why the voltage becomes constant after when this RL becomes 224?
Okay. No, if you can see that from this table, that your query is if the resistor is changing, why means basically you want to ask. Let me tell you. Yes. So basically in this case, V load is our VZ, because it should be across to that resistor, means it is in across to the register, and the total current which is coming through this input, that is divided into IZ and IL. Okay, so as we are changing the resistor, so depending on that IL is changing, but as IS equals to IL plus IZ, so as IL is changing, then IZ is also changing. But as this is a regulated supply, I mean regulated source, means a Zener diode, it will maintain a particular the current across it, as you can see, current across and also voltage that is having some particular limits. So VZ, there is in our case VZ was 5. So in this case, as you can see, so that your total source current is summation of this load resistance and load current and Zener current. And if we put this value, then you will have that final value of output voltage, that is equals to Vi minus Is into Rs. Okay, so that is independent of your load resistance. So that is why you can say yes, but the load resistance should maintain this condition. RL should greater than RL minimum. Okay, why? Because if you just put go through this one, let's say for this one, if we put that IL max, what will be the limit for IL maximum, IL current, maximum current, and IL minimum current? So RL minimum value is for VZ into RS divided by VI minus VZ. So in the that value, let's say for this one, 224 is okay. Below 224, our voltage that load value is 150. So do you have pen and paper? Who asked this question? Please.
Yes, sir. I am with pen and
Saurabh,
paper.
yeah, please find out the RL minimum value for this one. For our case, VZ is 5 volt, okay,
Yes, sir.
and RS is our 505, I think, right? Yes, 505.
Yes, sir. Okay.
and then
Please.
input voltage minus Vz.
Yes, sir.
So Vz is our 5 volt, and input voltage at that time, input voltage we have set at 20 volt. Okay, please find out.
168 point something. 168.7.
It is coming 168 point something.
Okay, very good. So that is why, as we have considered this value 150, that is less than our RL minima. That is
Yes,
why,
sir.
yes, that is why the voltage, as you can see, that is equals to input voltage. From this relation, as you can see, there is two conditions. If RL is less than RL minima, then our output voltage will be similar to the input voltage. When the RL is greater than minimum voltage, minimum RL, then output will be in this form. Okay, that is basically equals to Zener diode. So that is why, as beyond 24, the voltage is constant. Did you get it,
Understood,
Saurabh?
sir. Yes, sir. Understood.
Okay, so if we just change the, and let's clear it, and okay, now we are having different set of value. Let's say Vz is or Vz is 5 volt. Let's take 10 volt. Okay, 7.5. That will be more convenient. Okay, 7 volt. Okay, so Vz is 7 volt, and our input voltage is how much? Let's say 17. Okay, 20 again, and Rs is now calculate the RL minima for this configuration. Yeah,
Sir, wait
equation
a
is
second.
this
I'm
one.
calculating.
Equation is this one. RL minima equals to Vz into Rs by Vi minus Vz. Vi is the input voltage, Vz is the general voltage, and also Vz is also here, and Rs is the source. You first of all, you note down the equation, then I am telling you the value. In our case, Vz is 7 volt, Vin is means Vi is 20 volt, and the series resistor is 400 ohm.
Sir, it is 215.4, sir, for this configuration.
Okay, 215. Okay, so that is why, as you can see, we have considered 150 ohm. So it is giving the same as input voltage. Let's change it very slightly. How much we are having? 180. Okay. For 180, oh sorry, for 169, again we are having 20 volt. Let's change it to 30. Then you can see the changes. It is in general voltage. Okay. So this is the
Yes.
reason, that is why it is we are having this kind of nature. Okay, is it clear?
Yes, sir. Yes, sir. Clear.
Good. Now we'll draw the circuit from this multi-sim one. I already told you. So let's first draw that line regulation. No, first the Zener diode one. Okay, and Zener diode characteristics. So for that we need a DC voltage source and we need a diode, Zener diode, and one resistor. Okay, and meters we need, right? 2 meters. Okay, let's draw the circuit first. Oh, sorry. Now this end will be connected to the P side will be connected to the N side. Okay. So as you can see, as we have considered this Zener diode, the corresponding Zener voltage is given. So in this case, we can change the voltage and we can have the output voltage. Now we need two particulars meter. So, okay. So yeah. So initially, what we are going to do, it is in, okay. Could you please tell me which bias it is in? Our Zener is in which bias?
Sir, it is in reverse bias.
Okay. So should we go for forward bias first or reverse bias? Okay, as we have make the connection for reverse bias, then please try. Means we are going with reverse one. Let's check the value at 500 millivolt. The resistance is, let's say, 100 ohms. Okay. Now play it. Error is given. No. Okay, no ground found. We have to give ground. Okay. So we have connected the ground one. Okay, what kind of data we are having? That is in 200 millivolt and one is 199 millivolt. Okay, let's change the voltage first. Then we can have, let's okay, let's change the voltage up to 1 volt. One volt. Why it is not showing that? normal auto. No. Okay. So let's stop it and please note down the value that our output voltage is 999.98 millivolt and input is this. Okay, sorry, we are supposed to, sorry, we should measure the current, right? Not the voltage one. Sorry. You people also did not respond to me that we should measure the current IV characteristics should we measure. Okay, let it be. So make the connection. You should tell me at least that I forgot to mention this. We should measure the current, right? Okay. DC output that we have applied 1 volt, we have 200 nanoampere current. Okay, good. Now change it up to another 1 volt. Oh, sorry. Change it to 2 volt. Then simulate it. Okay, so we have 400 nanoampere. So could you please just note it down, then we'll plot it. Then we'll have a graph. I'm telling you the value. Any one of you, please note down the value. One column is for voltage, one column is for current.
Yes, sir, noting.
Okay, good. So first one is for 1 volt, 200 nanoampere current. And for the second one, for 2 volt, we have 400 nanoampere current. Okay.
Yes, sir. Yes, sir. Noted already.
Okay, good. Then let's move it further for 3 volt. Let's say. So for 3 volt, it's 600 nanoampere current. Okay. Now for 4 volt, or let's say 4.2 volt. For 4.2 volt, the current is 839 nanoampere. Okay. Now let's move to 5 volt. Saurabh, you are noting?
Yes, sir. I'm noting.
Oh, good. So 5 volt, that current is in microamps. 670 microamps. Okay. Now let's just have another 2-3 value, then we can have 6.25. No, it is in milliamps. So 12.529 milliamps. Okay. So this was for reverse bias. Okay. Now let's do it for forward bias. After that, we'll draw it together. So for forward bias, we have to make a connection from N side to the N. and P side to the positive terminal. Okay, good. Okay, Saurabh, please note down all the values. Let's change it to 900 millivolts. Okay. So for 900 millivolt, okay, it is in 3 milliamps. Okay, means we have to go beyond it, means below it. Let's say for 90 millivolt, yeah, it is in nanoampere. Okay, Saurabh, please note it down. For 90 millivolt, our current is 18 nanoampere.
Yes, sir, noted.
Okay. Then for 140 millivolt, then for 140 millivolt, still the current is in 28 nanometer. Sorry, nanoampere. Okay, now change the voltage further. Let's say 250 millivolt. For 250 millivolt, the current is 69 nanoampere still. Okay, now change it to 400 millivolt, and let's see the value. Okay, in 400 millivolt, the current is 4.79 microampere. Okay, now for 500, for 500,
134.
how much value? Yeah, for 500, it is 134 microampere. Okay, and now for 600 millivolt, yes, for 600 millivolt, yeah, the current is 703 microampere. And for, let's check for 800, for 800 millivolt, the current is in ampere, milliampere, sorry, 2.3859. Okay, 2.38 milliampere. And you had the data for 900 millivolt, right?
Yes, sir.
Okay, then good. So we have both the data for reverse and forward bias, right? Now,
Yes, sir.
okay. So please tell me, I will draw it. For this. Yes, please tell me the data.
Sir, first of all, for reverse bias. No,
Yes,
sir.
yes.
Sir, first is 1 volt, 200 nanoampere.
Okay. 1 volt, 200 nanoampere. Oh, you are telling in this way. Okay. Minus 1 volt, 200 nanoamps, right?
Yes, sir.
Okay. And maximum current is in milliamps. Okay.
So
So
maximum.
current is milliamps, right?
Yes, sir.
Okay. So 200 nanoamps. Okay. Next value is
2 volt, 400 nanoamps.
2 volt, 400 nanoamps. Okay, good. Next. Minus
Similarly, sir, minus 3, 600 nanoamps.
minus 3, 600 and -4.
Sir, it is not for -4, it is instead -4.2, sir.
Okay, -4.2. It is
840 nanoamps. 840.
840 nanoamps. Okay.
Sir, it is 5.
Yeah.
677.35 microamps.
673.5.
Sir, 677.35.
0.35 microamps means -6. Okay,
Yes.
good. Then any other value? Yes.
Sir, it is for 6.25.
6.25. Yes.
It is 12.6 microamps. Sorry, milliamps.
12.6
Milliamps.
milliamps. Okay. Any other data?
No further value, sir.
Okay. So this is for reverse bias, and let me add for forward bias. Yes.
Yes, sir.
Hmm.
Sir, for forward bias, it is first is 90 millivolts.
90 millivolts. Okay. And maximum voltage is in milli, right?
Yes, sir. Millivolt.
Okay, then wait. Okay. 90 millivolt current is
Sir, 18.03 nanoampere. So you can take it as 18 also.
18 nanoamperes.
Nanoamps.
Okay, good. Next,
Sir, 140 millivolts.
140 millivolts,
So 28.2 nanoamps.
28.2 nanoamps. Okay, good. Next,
So 255 millivolts.
255 millivolts, and the current
It is
is
69.16 nanoamps.
69.16 nanoamps. Okay, good.
Sir, 400 millivolts.
400 millivolts,
4.8 microamps.
4.8 microamps. Good. Next,
Sir, 500 millivolts.
500 millivolts,
135 microamps.
135 microamps.
Sir,
Okay.
600 millivolt.
600 millivolt,
703.45 microamps. 703.45.
microamps. Okay, good.
And the last one is, sir, 800 millivolts.
800 millivolts,
2.38 milliamps.
2.38
Milliamps.
milliamps. Okay.
Yes.
901.
So it was 3.30 milliamps.
Okay. Okay, now let's plot it. So this one is voltage, and the unit is in millivolt, right? So
Yes, sir.
and all these are in amperes. Or else we can have a milliampere scale or ampere scale. Okay, just leave it and we'll change over there. Current, and this is also voltage and current. It will be in volt only, and the current is in ampere. In this case also ampere. Okay, so first draw it for, oh sorry, one second. My screen is visible to you?
No, sir.
No, sir.
Sorry, one second. Now I think it is visible, right?
Yes, sir.
Yeah, good. So Let's plot it. Yeah, good. So this is voltage is in millivoltage. Okay. So this is our expected graph for forward bias. Okay. As you can see, you can make it little bit better. No, that's not a part of your thing, but still, let's say. So I think you are familiar with this curve, right? This is forward bias diode, PN junction diode. But the cut-in voltage, as you can see, it is very less. What is the cut-in voltage for normal silicon PN junction diode?
Sir, 2.3 volts, sir.
Cut-in voltage 2.3 volt, silicon. From where you get this data? Cut-in voltage for silicon or germanium for different diode, it was different. We have discussed already, right?
Normal PN junction diode.
Silicon diode or germanium diode.
Sir, it is 0.7 showing on Google, sir.
I know it is 0.7 and
Yes,
I
sir.
know
That's why I
Google can-
searched. I googled for my satisfaction. I said Google.
Okay, but you should remember yourself. Okay, very good. At least you have used that. You thought that Google can answer. Okay, and this one will be minus current. Yeah, that is for silicon. It is 0.7 volt, right? Yes. So this is another beautiful nature of the graph. And if we want to see, so you got it, means are you getting this means this one, the simulator and how to simulate it and how to have the data? Is it clear to you people, or any other query do you have? So actually this current should be negative, means in comparison with that initial one. Okay. So now if we want to put them together, then this voltage should be divided by it should be in voltage, means the scale should be same, right? So then we have to divide it by 1000, then the data is good. So now could you please tell me what is the cut-in voltage for this Zener diode in forward bias, and what is the reverse bias, means breakdown voltage for this? Sorry, 1 second, little bit issue is there. Yeah, our this voltage should be, this should be reversed. Yeah, please tell me what is the cut-in voltage for this Zener diode?
Sir, 4.2, sir.
4.2 means which one you are telling? That the forward one means breakdown, or
No, sir, for reverse bias. Sorry, reverse bias.
okay, means breakdown voltage you are telling, right?
Yes, sir.
Okay. So now is it quite bit little bit similar? That graph I have already shown you that, no, not from here, that Zener diode characteristics.
Yes.
So, but it was not available in that VLab one. So you can simulate it, and so you can have yes this curve, right? In a same window, means as it is in your textbook also, that forward and reverse one in same window, right? So, oh, I think you didn't get that one what I was sharing. Yeah. Yes, it is quite similar with this one, right? The initial the IV characteristics of Zener Diode, which I already shown you.
Yes,
This
sir.
is for forward bias
Yes,
region
sir.
and this is for reverse bias region. And we are having that similar nature here also. That in case of forward bias, we have less points. That is why this value is this and this in this way. Otherwise, we can have the smooth curve for that one. Means similar to the exactly similar to the experiment. Sorry. Okay. So that is the beauty of this simulator. So you can simulate anything, any circuit. Those who are basically EC people or and whatever circuit you have go through in your textbook or whatever it is, you can just verify it. You can draw it and you can verify it. Okay. Okay. Any query till now? Do you have? Please ask. I know most of you are not listening. Just joined and let it be in this way, but still those who are in line online, then you can ask.
Sir,
No,
can we plot a graph in
sorry.
multi-simulator? Can we plot the graph in this multi-simulator?
Yeah, for that specific one actually I don't know. Means I
Means
have to.
we are building the circuit in this multi-simulator.
Yes,
So,
yes, obviously you can, that in that one. Okay, I already shown you that half wave rectifier and full wave rectifier one, that those things. Let me show you that one. Okay, save this as a Zener diode. Okay, then I'll show you. Obviously, here is the grapher one is here. So through that one you can plot it. This one you can plot it. But for this specific case, I don't know how to do it. But I think if you people search it, I mean explore it, then you can have. Okay, let's say for this one, half wave rectifier. So basically, these simulators are real life kind of simulator. Means if you apply it exactly to a circuit, then depending on the time, they will show you the output. It means in your lab. And in this case of this simulator also, depending on time, you will have the values of input and output as well. So as in this case, we are having a constant voltage DC voltage source and DC output also. So in that one we have to note it down the data and we can plot it, but I don't know whether it is means maybe it is possible, but I don't know right now. Yeah, as you can see here, we can plot this graph. If you just simulate it, then you will have this graph. Okay. Okay, is it clear?
sir, once again, please show it how to simulate it.
Yeah. Okay, actually first of all we have to draw the circuit, then we have to just run it. Then depending on the number of probe, so it will show the output of the probe. As you can see here, we have two voltage probe. First one is the input voltage one, and this one is the output voltage one. So depending on that means depending on that number of probe, so this is for output of that, or you can say result of that probe one. green one, and this blue one is the output of the probe for this probe output voltage. Okay,
Okay, sir.
so it will come, means automatically it will come, no issue. Means don't worry about that. But as for this case, we need a discrete value, so I don't know how to do that. Now I will try to tell you people if I find you in the next lab. I'll try to, but in the meantime you can explore it on your own if you find time. Okay, but it is possible. It is not like that it is not possible. Okay, okay, no issue. So after
Okay, sir.
that, we have to go to that line regulation and load regulation circuit, right? So we can draw it here only. Okay, so till 4 we have time, right? So if only we can have, we can perform that load regulation, sorry, load or line. Okay, only line regulation one, then we'll do that, and you people can explore that load regulation one. Okay, and if you have and find any doubt, then you can ask. Okay, so for line regulation, we have to draw this circuit, one series resistor, and oh no, this is for load regulation. Okay, so load regulation will be easier, I think, to if we just vary. We have to just remove this one, add another resistor, and that should be in parallel. And our regular convention is that if it is in parallel, then it should be in vertical position. But that is not the definition of parallel one. Parallel means all the terminals should be, means same kind of terminals would be connected in same place. From which perspective you are trying to, so see, observe the load, I mean observe the circuit. So load value, oh sorry, we need a variable load, right? So potentiometer, instead of this one we need this. So you have you drawn circuit, any circuit using this multi-sim one?
Along with it, just now I drawn, sir.
Mm-hmm.
Along with it, just now I drawn the previous one, Zener Diode.
Okay. No, but what about that previous lab? Okay, no potentiometer connection. We cannot have that particular connection. Okay, then let's connect that diode. Let's connect a resistor only. Okay, and we'll change the value of the resistance. Okay. Now, please tell me what should be our that minimum voltage for RL. Okay, let me fix it to a voltage of not 80 volt. So 20 volt. Okay, 18. Yeah, it is in 20 volt, and our series resistor is in 1 kilo, and Zener voltage is 5 volt. So what should be our load minimum load value? using this formula calculated. This one, Vz into Rs upon Vi minus Vz. Please tell me the value.
Sir, RS was 100 kilo ohm.
No, not 100 kilo, 1 kilo. Let me rename it. This one is Vi and this one is RL. And this one is RS.
So 333.33.
Sorry?
0.33 kilo ohm, sir.
Okay, 330
Yeah,
ohm.
yeah, yes, sir.
Okay,
333.
good. So then we have to keep it in below that to have a particular data for that one. Okay. So we need, what do we need in case of load regulation? We need to measure this load value, means resistor value, and the output voltage. Output voltage obviously across it. So let's remove it from here. Let's connect. What is 1 second. Okay. Now just have some data for this value. Okay. What is this one? V2. Okay, please note it down. Then we will see. Any one of you, please note it down. Noted?
SF0651.
Okay. Then let's change it to 200. Sorry. Oh. Okay, you have calculated the value 330, right? So let's have another value less than that. And then simulate it. Yeah. Voltage is this much millivolt. Okay. Then change it to beyond 330, let's say 400 ohms. No, that should not be the case. No, something is wrong.
Copied.
No, that is wrong, I think. Load regulation, yes, this voltage. This is regulated voltage, output voltage across this RL. That should be different. I don't know why it is coming. Oh, sorry. Could you please tell me what is wrong in this circuit? I did some mistake, and could you please tell me what is that?
Sir, forward bias, I think so.
Exactly. So that is why it is not working. So remove all the data points. Then, so it is in forward bias. So if you want to have a special character from, means special feature from Zener diode, then you must put it into reverse bias, right? So you should tell me at least that It is in reverse. Sorry. Okay. So now make the cathode gets connected. Okay, good. Now change the voltage. Change the resistor value for two cases. One is for 100. Let's say for this value, let's check it. Yeah. Okay. As because it is 125 ohm, so the voltage is 2.2. Okay. Noted.
Yes, sir. Yes, sir.
Now let's change it to, let's have another value that is beyond 330, means below 330. Let's say 255. Then run it, and yeah, it's 4 volt. Okay. Now,
Yes, sir.
now for 400, the voltage is 4.960. Okay. Let's change it. 600, 4.9803. Okay, so it is giving much more realistic answer. The virtual lab one was giving that ideal one, but in this case it is giving much more realistic value. It's not similar exact to 5 volt, right? So let's make it 1 kilo. Still the voltage is same. Now take another value, 10 kilo. It's 4.9940. Okay. Now please tell me the data, then we can plot it. Okay.
So 125.
1 second, please. Yes. This one is the load in ohms. Yes. And this one is the voltage.
Voltage.
In volt, right? Okay.
Yes, sir.
Please tell.
125. Yeah.
120.
5.
125.
2.22 volts.
0.22 volts. Okay.
255. 255 ohm.
255.
4.0636.
Okay. Next.
405 ohm.
405.
4.96.
4.96. Okay.
Next 655.
655.
4.99.
4.99.
98.
98. Okay.
Next 840.
840.
4.984.
4.984. Okay. Then
Next 1 kilo ohm.
1 kilo. Okay.
4.986.
4.986. And 10 kilo, right? Then 10 kilo is there, right?
Yes, sir. 10 kilo ohm.
4.99.
4.99.
Okay. Now plot it. My screen is visible to you, right? Yeah. My screen is visible.
Yes, sir. Yes, sir.
Okay.
Yes, sir, it will help.
So as you can see, this is the similar curve that we obtained from a virtual lab. Means that that was ideal one, but in this case, it is a realistic one, much more realistic. I think this curve, yes, this one. So as you can see, what is the difference between these two curves? So that is why this simulator is giving much more realistic answer. So it will be very helpful for you people if you are going to have some experimental project, and before that you need a simulation, and from there you have a realistic result at least, not the ideal one. But ideal one is also good. But in virtual lab, limitation is that you cannot have your own customized circuit. But here, whatever you want, you can draw it. So this is for load regulation curve. Okay. So any query? I think you can draw it for the, I mean, do it for the line regulation one. Is it? Or
Yes,
we'll,
sir.
I think you can do it, right?
Yes, sir.
Okay. So do you have any query related to this lab? Okay, only have 20 minutes left. So if you have any query, you can ask, or else we can conclude our session for today. Do you have any query?
No, sir.
Okay, good. So thank you. Thank you for attending.
Thank you, sir.
Thank you, sir.
Thank you, sir, for such nice explanation, sir.